We are happy to have Biswajit Sahu from King's College London. He'll be talking about gravitational waveforms and constraining quantum field theories. Biswajit, you can start.
Thanks. I think you can hear me, right?
Yeah, we can hear.
Okay. First of all, thanks me thanks for inviting me to give this seminar, and unfortunately, I could not able to be there. But today, I will try to speak about some set of research works under the theme scattering amplitudes, and hopefully I will able to convince that even there are some relevant work still in 21st century people can do related to scattering amplitudes which will have some larger impact. So, and please don't hesitate to ask any questions at any point, because I think clarity matters more than finishing on time. So even if I go a bit over time, I can cut it off, but please stop me at any point. Okay. So first, just keeping in mind that possibly there will be high energy physics community in a broader sense, though this will be a very technical seminar, first I will try to give a bit overview of the presentation, which with a very less number of equations and a bit non-technical way to set up the stage before going to the more technical part of the seminar. So I'll start with some very basic things we learn in quantum field theory is the scattering amplitude, which is the framework we use often in quantum field theory. So we define it as some unitary time evolution by some interacting Hamiltonian from some free asymptotic state in the very past to some free asymptotic state at very far future. And the modulus square of this S matrix element determines the transition probabilities between given initial state to some final state. And when the quantum field theory is weakly interacting, we can compute the scattering amplitude perturbatively using Feynman diagrams, and this turns out to be most often the most efficient method for weakly coupled quantum field theory. And there has been a lot of success using S matrix in last century, like for example, starting from the discovery of Higgs boson in proton-proton collision to various precision tests and discovery of new particles in LHC, for example, understanding of quark-gluon interactions and asymptotic freedom in QCD, and even the birth of string theory happens to trying to develop Regge theory to understand the high energy hadron scattering. So there has been an enormous number of success. Now we can ask, coming to 21st century, what we can do new and relevant. And as I will explain, there are two things we can do and still it is relevant in this modern era. One is basically we can compute the classical gravitational waveforms using various perturbative techniques of scattering amplitude, considering gravity as an effective field theory. This will be one of the topic of my seminar. And then another thing is that when the strength of the quantum field theory, the interaction strength of quantum field theory is not weak, but instead strong, we can develop some non-perturbative techniques to study quantum field theory. And one of such example is the bootstrap, like the S matrix bootstrap is one of such example. And these are the two topics as I'll explain, and let me go a bit more deep into it. What are the questions I would like to ask in these two areas? So the first part, this is basically deriving gravitational waveforms from some scattering amplitude techniques. These are the set of works I did with this set of collaborators whose names are listed here. And let me give first the basic classical questions which you would like to answer before going to use S matrix. So for example, consider a classical astrophysical scattering event. For example, a violent explosion where a bound state system breaks apart, ejecting matter at very high speed. This happens, for example, in type 2 a supernova explosion where some neutron star produces and some high kick velocity gets from some excess neutrinos ejecting in the opposite direction. Or you may consider a set of objects which come together, interact, and then fly apart, possibly exchanging various quantum numbers. This happens, for example, in bullet cluster, where a pair of galaxy clusters passes through each other. And in all this astrophysical scattering event, if we place a detector at large distance, in principle, we should observe gravitational wave. Hence, it will be interesting to compute gravitational waveform even for scattering event, though the recent focus is mostly looking for the waveforms for merger events. However, computing this detailed gravitational waveform could be very complicated, because when the objects are close to each other, they may interact via various short-range forces, which may include nuclear force, Fermi pressure. This is what happens, for example, in the case of supernova explosion. Or even they interact solely by gravitational force, like for the case of black holes. It could be very strong, and one may need numerical relativity to solve the Einstein's equation. However, as I will show, classical soft graviton theorem, this will be one of the first part of the topic of the first part of my seminar. This basically provides an analytical way to compute the late and early time parts of these gravitational waveform templates, irrespective of all difficulties. And this provides some universal prediction for gravitational memory, which will be observed in recent future. And for example, what I will show is basically I will start from some quantum gravity S matrix, some low energy properties of quantum gravity S matrix, which we call the soft graviton theorem, and then taking some soft coherent and classical limit, we can able to extract the gravitational waveform in low frequency or in late and early times, which is known as the gravitational memory, starting from the S matrix soft theorem relations. Also, we will provide some independent derivation of this late and early times part of the gravitational waveform by iteratively solving Einstein's equations and trajectory equations, and those has one-to-one relation of this quantum setup, as I will explain. So this will be the kind of broad overview of the first part of my seminar will be. Now, let's go to the non-perturbative setting of the quantum field theory. So there, like I also did some work with a set of collaborators whose names are also listed here. And there, I will study QFT in a non-perturbative setting, considering this quantum field theory is any arbitrary point on the renormalization group flow trajectories flowing between two fixed points at very high energy, some ultraviolet fixed points described by some UV conformal field theory, and in the low energy it is described by another fixed point described by infrared conformal field theories. And I will treat quantum field theory as some arbitrary energy scale, some points at some point on the renormalization group flow trajectory. And the broad question we would like to answer here is that given some quantum field theory at some energy scale, what is the space of possibly UV completion consistent with some reasonable assumptions, like for example unitarity, crossing, analyticity of the S matrix. So this kind of inverse RG question we will ask, knowing some low energy spectrum of quantum field theory, can we use some kind of like physical principles valid at all energy scale able to constrain the space of UV conformal field theories. And the tool I will use to explore this question is basically the S matrix bootstrap, and also sometimes it also combined with some spectral density and some form factor bootstrap. But the idea of bootstrap is that instead of solving a particular theory, what we will do, we will constrain the parameter space of all allowed theories based on physical principles. And you don't need to rely on any existence of Lagrangian in this case. Only you need to have the consistency between some analyticity, crossing, some high energy behaviors, unitarity, and other properties. And just pictorially, for example, the unitarity of the S matrix, which we usually learn as optical theorem, can able to allow some section of parameter space of a quantum field theory, and outside this allowed region, if you give the quantum field theory parameters some value, this theory will not be compatible with the like physical principles, I will assume. So this is kind of the main philosophy of the bootstrap, and in this philosophy, like we want to, since this is a scattering amplitude bootstrap or the S matrix bootstrap, in the renormalization group flow setup, if we want to implement that, then we need to ask like the following question: that can we able to identify a set of observables first for any renormalization group flow, which are completely determined by the UV CFT and the IR CFT data and do not depend on the details of the RG flow. Those we will call the protected observables. And if those protected observables are the S matrices, and in such cases where suppose the IR CFT is trivial, that is the quantum field theory is gapped, so the IR CFT is empty, we can use those S matrices to bootstrap and put constraints on the possible spaces of UV CFT. And this is the philosophy which I will follow. And for example, one of the questions we asked is basically that, say, considering a 4-dimensional RG flow by some relevant deformation of the UV CFT, and we can compensate this explicit conformal breaking introducing some dilaton field and then flow to IR. And suppose if we consider a quantum field theory which has the lowest stable particle is a massive scalar, then the IR CFT is gapped, and we can ask that can we able to constrain the parameter space of UV CFTs. And one of the constraints we can put on one of the CFT data, which is known as also A anomaly, which also appears in some 3-point function of stress tensor correlator. So you can think of it as a OPE coefficient of a appear in the 3-point function of stress tensor. So we can able to constrain the space of values of this AUV, which can flow to such a gapped quantum field theory. So these are the questions we could able to ask using this S matrix bootstrap. Another question I will also another problem which I will also discuss in a more technical way in the main part of the seminar is basically what happens, suppose if we have a conformal field theory with some global symmetry and we put it in a strong magnetic field. So can we able to put some constraint on the magnetic susceptibility, magnetic transport coefficients of a CFT in strong magnetic field? So here you can think of CFT in a strong magnetic field is again a renormalization group flow. However, it breaks Lorentz invariance because we placed a constant background magnetic field. But you can think of it's basically deforming a UV CFT by basically its current operator, which is again a relevant operator, with the coupling to the current operator given by some gauge field with a field configuration which gives a field strength which provides the constant magnetic field. And in general, since there is no other scale, actually for interacting CFTs always they become gapped, and the mass gap is given by square root over a magnetic field, and IR is a empty IR CFT. So again here we will develop some effective field theory techniques and finally able to find some effective field theory at the IR involving some background fields, and able to answer the question that are all magnetic susceptibility and transport coefficients allowed at strong magnetic field, or can we able to constrain them? So these are the rough questions I would like to answer in this seminar, and maybe I should stop here if you have any questions for the overview part.
You can continue.
Okay, thanks. So now let me describe the first part of my seminar, which will be soft graviton theorem and gravitational memory. So I will start from the quantum soft graviton theorem. So take a generic theory of quantum gravity in asymptotically flat spacetime with 4 non-compact directions. Okay, and now in this theory of quantum gravity, consider a generic scattering amplitude with scattering of some arbitrary number of particles. They could be any reducible representations of this 4-dimensional Lorentz group. And suppose this scattering amplitude also contains an external graviton with momentum k and the polarization epsilon. And now take this amplitude and take the energy of this graviton, which I denote by omega, to be 0. So what happens is that this scattering amplitude factorizes into a scattering amplitude which does not contain the external graviton, and the part which multiplies this amplitude, which we call the soft factor, turns out to be universal. In a sense, it is only determined by few scattering data and does not depend on the details of how you complete your quantum gravity. Obviously, it is not all. There will be also some non-factorizable subleading terms, but those will be subleading in the small omega expansion. In a sense, the expressions written below. So the part which usually factorizes has the following behavior in small omega expansion. It goes like omega to the power t log omega to the power t plus 1. T runs from -1 to infinity. So it has like 1 over omega, omega log omega square, those kind of terms which factorizes, and the coefficients are universal. On the other hand, the non-factorized parts has the behavior is like, as you can see, it's like one less, like it has omega to the power t, but the powers of logs are less than the universal piece, which is like the t plus 1. And in general, these parts for a all loop order S matrix cannot be written in terms of the amplitude, which does not carry the external graviton. So this is the statement of soft graviton theorem. Very good. So now let me show different terms in this soft factor expansion. So as I was telling, the leading soft factor, which is this 1 over omega coefficient, has already been derived by Weinberg in 1965. After that, there has been many attempts to extend this and go to subleading orders. However, due to the infrared divergence issues of loop corrected S matrix, people has to restrict themselves for the tree level S matrix, and what they found is that there is a corrections to this which is polynomial in omega expansion. Like say omega to the power 0, order omega, this is the kind of contributions. But once you include the loops, one have to first resolve the IR divergence issue, as I will explain in the next slide. But if you do it carefully, what you will find is that compared to the tree level omega to the power 0, in omega going to 0, there is a more dominant contribution at subleading order, which goes like log of omega. And then the next order is like omega log omega square, and those are the contributions at the soft factor takes. And it took a long time because just how to find this IR, like how to find this soft factor which is IR finite, and how to take care of the loop corrections was a challenging problem. And just to mention is that all the earlier derivations of this omega to the power 0 and this order omega, all these contributions, though they factorize at the tree level, but once you include the loops, they don't even factorize. So those goes into the non-factorized parts of the non-factorized part of this soft theorem expression. Very good. So now, what was the challenge and how we resolved this issue to derive, for example, this log omega soft factor? So what we realized first is the fact that soft factors are defined as ratios of two amplitudes with and without the soft graviton. And also what Weinberg's already taught us, that the IR divergences, like for perturbative gravity, basically exponentiate when you sum over the loop diagrams. And however, the amplitude which contains the extra soft graviton includes some additional divergence compared to the diagrams which do not contain this external graviton due to some self interactions between the gravitons. So I have to take care of all these issues, and then finally, while deriving the soft factor, you have to take the ratios of the two amplitude, cancels out this IR divergence, and regulate this extra divergence appeared in the for the Feynman diagrams associated with the scattering amplitude with external graviton. And then finally carefully analyze the IR finite part and then take the soft limit. And to do all these things step by step and systematize, what we need to do is basically one needs to generalize this Grammarian decomposition prescription which has been developed for QCD, like for computing Sudakov form factor and many other things for the case of perturbative gravity. And this is what we did, and kind of finally analyzing the loop diagrams. For example, here I just explicitly wrote down the expression for this log omega soft factor with the particular coefficient. The structure is not important. The only important thing is that this is universal. In a sense, it don't depend on what kind of particles you are scattering or whether your quantum gravity theory has some higher derivative corrections or how you will complete. None of these informations affect the soft factor. And this is also one loop exact. So if you go higher and higher loops, you won't receive contributions for the soft factor. And similarly, the omega log omega square soft factor is also two loop exact. And similarly, this is how the structure looks like. Very nice. So now this is some property of quantum gravity S matrix, some infrared property which we call soft theorem. What it has to do with the classical gravitational waveform computation, which I advertised at the beginning.
Sorry, Vishwajit,
Yes,
could you sort of say a few words about how the derivation is carried out? Just the basic idea of how you get these expressions.
Yeah. Okay, thanks. Yeah. So it's just the fact that so for example, I drew some Feynman diagrams in the numerator and the denominator in this slide. So in what you have to do, so in the numerator, the diagrams which I drew, all of, like for example, the loop diagrams are infrared divergence. And in the denominator also the loop diagram is also infrared divergence. So what I have to do is what we did, we basically split the Feynman propagator of the virtual graviton to be two parts. It's just rewriting two parts. One we call some k graviton, one we call some g graviton. And if you compute any diagrams with these k gravitons, they are basically IR divergent. And if you sum over the loops, they basically exponentiate. It's kind of the iconal exponentiation one usually learned by taking some low momentum limit of the loop momenta and summing over the ladder and cross ladder diagrams. But here we cannot take this limit. Instead, we work with the finite loop momentum, like the loop momentum runs from 0 to infinity, but we split it, the Feynman propagator, in such a way that one part of it carries over the IR divergence speed and resum, and the other piece only contains the IR finite piece. And once we do that and cancels this, like the numerator and denominator like contributions up to extra divergence coming from the last diagram in the numerator, which on h to IR regulate, and then we analyze the finite piece and take small omega limit. And also there are two type of contributions coming to the log omega. One is when the loop momentum greater than omega in some region and some region smaller than omega. So I have to take care of all these contributions carefully to find this result. Maybe, okay. I don't know whether it's illuminating.
That's fine, it's fine. Yeah, thanks. That's one rough idea. Thanks.
Okay, thanks. Fine. So now I will come to the classical scattering event, and we'll try to relate how can one find gravitational waveforms from, like for the classical scattering problem with starting from the quantum gravity soft theorem results. So for that, let me consider the following classical setup. So here this is just a classical astrophysical scattering setup, you think. So say some m number of objects are coming in, which has some mass m prime, momentum p prime, spin s prime. If they have some like due to their size, there will be obviously some higher multiple moments, so like quadrupoles, there could be some love numbers. So all these informations are there, and those are the objects which are coming in, going through some complicated interactions in some region R, and then finally dispersed to n number of objects with the mass denoted by m, momentum p, spin s, and higher multiple moments. Okay, and we choose this region R to be sufficiently large, this is on us, so that all the short range forces, which may include splitting, fusion, or any other forces which falls up faster than the inverse square law, basically they basically are present only inside this region R, and outside only the long range gravitational interaction exists. This is how we split our space-time for this scattering event. And let's consider the size of this region to be L. So what will be our expectation if we consider this scattering event and try to find a gravitational waveform? So suppose from this scattering event some gravitational wave peak comes to a detector placed at far distance, and if we wait for sufficiently large time in unit of this length scale L, our expectation is that all the short range forces which decay faster than the inverse square law will no longer affect the parts of the waveform which are the late and the early time part of the waveform, which is compared to this length scale L. So the expectation is that the late and early part of the gravitational waveform should solely be determined only by few scattering data and don't depend on this detail of the scattering event happening inside this region R, because as we know, gravity is universal at long distance. So this is the expectation for this classical scattering setup, which I will make concrete mathematically as I go along. Okay, so here again I set up this classical astrophysical event, and suppose I have a gravitational detector at some distance r along some direction n hat, and let me define the deviation of the background metric from the flat space time by h mu nu. So h mu nu is the metric fluctuation at the detector, which is a deviation from the flat metric, and e mu nu I define as the stress reverse metric fluctuation. Just it's an invertible like equation from h. If you know h mu nu, you can know e mu nu. Now what is the waveform? So the waveform is basically first you can think of from this scattering event, the time the gravitational wave takes to reach the detector is basically the time it takes, which is basically the distance r over the speed of light. But since the gravitational wave is propagating in a curved background produced by the scattering event, so there will be also some gravitational time delay, and one can compute this time delay proportional to log of r, and then define sorry, then define the retarded time, which is the time passed after the peak of the gravitational wave reaches to your detector, which I'll denote by the u. So then the time will be replaced by u plus r over c plus this gravitational time delay correction, and then r of n hat. Now take this mu nu at fixed u and take large radius limit. So large r expansion. And so this 1 over r coefficient, which we usually often call the radiative mode of the gravitational waveform, this is what I will call as the gravitational waveform, and this will be our interest to determine. So this, and which is a function of only the retarded time u and the direction of gravitational emission n hat. Okay, so or we can do a Fourier transform in this u variable and go to frequency space. And I'll also denote the frequency space gravitational waveform by this e tilde mu nu, which is a function of the frequency of the gravitational waveform detected, and also the n hat, which is the direction cosine between the scattering event and the detector. So this will be our interest, and I will only able to determine these parts of the gravitational waveform for large values of u or the small value of frequency omega. Due to this, because I am only interested about the universal part of the gravitational waveform, which only determined by the scattering data, as I explained in the earlier slide as an expectation. And now to relate it to the quantum gravity, like the soft theorem relation, obviously if we are interested about some classical gravitational waveform, a single graviton cannot produce a classical gravitational waveform. What one have to start is basically you have to start with some multiple number of graviton emission and study the soft theorem there, and that you did in d greater than 4, and then you have to take a coherent limit that all the soft graviton are emitting in a coherently along some particular direction, and then finally use this finally take the classical limit. And if you do that and compute, for example, the energy flux for such kind of a quantum mechanical scattering event, and then take classical limit and find the energy flux of the graviton emission in the classical limit, and then independently compute the energy flux knowing the waveform and compare this, then what you will find up to some undetermined phase, basically the frequency space gravitational waveform contracted with the polarization tensor turns out to be proportional to basically the soft factor, which we derived like from the quantum S matrix, and this is turns out to be only a soft factor for a single soft graviton emission and its classical limit. So once you know, then basically this single soft graviton emission soft factor and can able to find the classical limit, you can use this formula and able to read off the low frequency expansion of the gravitational waveform. Very nice, but this works in only d greater than 4. In 4D, due to this infrared divergence issues I mentioned earlier, this whole like derivation breaks down, and it is also not clear how to find this S classical knowing the quantum soft factor in 4 space-time dimension. However, we can independently compute this gravitational waveform setting up this classical event and then try to see which parts of this quantum soft factor through this relation contributes classically. And if you do that, we get this following observation, that while computing the soft factor in the quantum gravity S matrix, you have to just do a simple thing. You have to replace all the virtual graviton propagator, which are the Feynman propagators, by its retarded propagator. Because classically, we usually solve retarded propagators due to causality. And so once you do that, you will be able to find this classical soft factor, use this formula, and read off the waveform. That's very nice. Now once you obviously know this formula and suppose know the soft factors, you can find the frequency space waveform and do Fourier transform to go to the time space.
Vishwajit, I have one thing. So like for 4-dimension use, you got this rule, right? Changing the propagator, right? Why don't you, I mean, if I do that for higher dimension?
Yeah, I think in higher dimension you also had to do this. It's just the fact that in higher dimensions, when like this Lambda and Sen, they try to derive these soft factors, so there the loops are not affecting up to the order they consider. So they consider up to order omega, up to subleading order, and the first loop contributions comes to this soft factor is like at omega to the power d minus 4 log omega. So what happens is that so while they analyzing this limit, they had to restrict, say, up subleading order, they had to restrict to dimension 5, and subleading order to have this, they had to restrict to dimension 6, so that they did not see the loop corrections and through the soft factor, and this prescription works. However, if you want to get the classical soft factor there in d dimension, this problem or this replacing Feynman by retarded propagator will appear again in say if you go in omega expansion, like as I was telling, the first loop correction will appear as omega to the power d minus 4 log omega. So they did not just see this effect. Yeah.
Whenever you have to do the loop computation, you have to do this change. That's what you're
exactly.
saying.
Right? Yeah. When the loops will contribute to the soft factor to the omega expansion up to that order, you have to do this change. Yeah.
Okay, thank you.
Now we have a very now we developed an iterative procedure where you can see actually that how exactly loop Feynman diagrams are one-to-one with the classical computations. It's just you have to replace Feynman by retarded, and it works so nicely.
I see.
Yeah, but it's just they could have seen if you in higher dimension as well, but up to the order the soft factorization happens, loops was not affecting the soft expansion. That's what happened.
Sorry, can I just ask one question?
Yes.
So this multiple number of coherent soft graviton that you have, how do you set that up in the calculation? How do you get the multiple emissions that are coherent?
Oh, so first we take with say some m number of soft gravitons are emitting from some scattering amplitude, and then we take this all the m number of gravitons to be emitting along some particular direction n hat with some solid angle, say omega, which is a small solid angle.
So is that like multiple, meaning like you just sum up many emissions from a leg or something? Is that what you do? Or
no, so from the scattering amplitude, it may emit not only from the external leg, it may emit from some internal legs also. So this will be a multiplicative factor. So for example, the Weinberg soft factor, it's just very simple. It just becomes m number of Weinberg soft factor multiplying. But since those are bosonic particles, so in the flux, you have to then divide by 1 over m factorial. And this is what basically happens in the coherent limit. Basically, that classicalized. It's like soft factor to the power m over m factorial. This is how it goes. And then when you take m going to infinity limit, you can do a saddle point approximation, and basically this energy flux basically peaked around the value of the soft graviton number, which is equal to the soft factor square actually. And from there you can classicalize and able to find this classical energy flux for soft graviton emission, and then compare with the classical energy flux and find this relation.
So the last line is saying that thing, or is that something else?
No, the last line is just telling that instead, suppose this is the procedure which one follow in d greater than 4 to get this relation. But the last line is telling that in 4 dimension, we don't know how to find this classical limit from the quantum soft factor. So this has not been derived because of the IR divergence issues. So this is just an observation we made. We computed the quantum soft factor independently and the classical waveform. So both sides of this first equation we computed independently, and this is the observation we made. And then using this observation, we can go along and find this result, whichever order we can go.
So this is saying take the on-shell limits of the virtual graviton, or is this saying something else?
No, this is actually telling that the finite energy particles put them in the on shell, not the graviton to be the on shell.
So it is saying put them on shell, right?
Yes, putting the finite energy particles to be on shell, like the virtual finite energy particles propagator to be on shell. So basically, Feynman propagator has 2 poles, right? When you deform the cell energy part of it, so you have to choose the pole which corresponds to the radiative mode, correspond to the retarded propagator. So this is what it is telling that.
Okay, all right. Thank you. Yeah.
Thanks.
One more thing. Sorry. So if you, given that you understood this, now at least we have a rule. So now can you start from the computation, the quantum computation, and interpret it as a regulator way of regulating things? Like, can you derive it, or is it something that
this fast form, like in 4 dimensions, the fast formula I wrote?
Yeah. So the last change, can you obtain it from the quantum calculation, given that you know that this actually works? So is it possible?
I think like one way is basically like, okay, this has not been derived, but one way to see is basically what happens, when you take this classical limit from some quantum, what happens is that it basically turns out to be, you have to take the mass of the object scattering is much larger than the Planck mass. So this basically corresponds to when once you restore the H crosses in your quantum field theory computation. So one of the pole contributes, like basically replacing Feynman by retarded propagator means you are taking only contribution from one of the poles of the Feynman propagator, one of the poles of the Feynman propagator. So the other poles will be suppressed by H cross somewhere. If you replace all the masses and the parameters as Planck mass and the original mass of the particle and take this ratio, so somehow my feeling is that it will automatically come from like in the loop computation, if we just treat this, if we restore all the H cross and write everything in terms of physical masses over Planck masses, this is the limit, and then it should come automatically. But yeah, this has not been explored much. Only using KMOC formalism, Alok and collaborators try to explore it, but there also it works only when the final momentum at leading order is same as initial momentum, so they had to go higher order to see this effect. But yeah, it's still unsettled, like how to derive it. It's not fully settled yet. Yeah. Okay, so now I'll try to first summarize the results of the gravitational waveforms in like going to time space, just doing Fourier transform from the going from frequencies to time space. And if you do that, these terms which I was telling, like 1 over omega, log omega, omega log omega square, all these terms, basically if you do Fourier transform, the 1 over omega piece basically gives a contribution a mu nu to the waveform at u going to plus infinity. Then the log omega generates this coefficient 1 over u both at u going to plus infinity and minus infinity. The coefficient I'm just calling b mu nu and c mu nu. Omega log omega square terms contributes to this log u over u square terms, and there is also a omega log omega order which is only determined up to first post Minkowskian order. They contributes to 1 over u square tails. And this u also is basically the retarded time. Now I also explicitly wrote down what is the gravitational time delay contribution to it, only determined by the outgoing particles momentum. Okay. So now what are the physical interpretations of this like gravitational waveform expansion in large U? So this mu nu has already been known from 90s actually, and this expression I just explicitly wrote here, and as you can see this is exactly proportional to the Weinberg-Schopf factor. What it does is basically that if you place the gravitational wave detector far from the scattering region and wait for a long time after the peak of the gravitational wave, actually at infinite time in principle, then basically what happens is that these mirrors of the gravitational wave detectors don't reach back to their original position. Instead, there will be a permanent displacement. That is why it memorizes that some scattering event happens and some gravitational wave passes through it. And what it memorizes is basically this permanent displacement between the mirrors, and this is known as the gravitational static memory. And just a key point here is that in this expression, when I am summing over the final particle state, where the sum a equal to 1 to n is the final number of final particle state, since in any generic scattering event, there will be also some finite energy gravitational wave emission is happening. So this sum includes an integration over the flux of the gravitational wave radiation as well, and this is known as the nonlinear memory. And this is present and non-vanishing, and this basically makes this mu nu expression complicated. So basically you don't just have to know the ingoing and outgoing particles information, but also the finite energy gravitational wave radiation to implement this formula in the observational setup. However, as I will explain, this coefficient b mu nu and c mu nu, which are the tail terms, this 1 over u coefficients, they have also this explicit formula only determined by the ingoing and outgoing particles momenta and the direction of graviton emission, which I'll denoted by the n mu, the null vector. And their expressions, as I'll explain, actually the massless gravitational emission can be completely rewritten in terms of the massive particle information. So this nonlinear part of the memory won't appear or can be simplified and can be written in terms of fully linear form. And just to mention, actually some limits of this expression has already been known in some form, not in form of gravitational tail memories, by some old papers by Peters and Blanche and Damour. and also like while taking this knife substitution rules in 4 dimensions, some non-relativistic and some particular probe limits has also been discussed earlier papers by Ladda and Sen. But this is a completely relativistic formula with in any generic setup it works. And finally, like this formula has been tested in different limits like massless limit, probe limit, and many other limits has been tested by many of the authors recently. So just to give this feature of this coefficient b mu nu, which is this 1 over u tail, is basically that, as I was telling here, you can manipulate this formula. So obviously this formula, the sum over the final energy particles, again includes the massless gravitational radiation, but you can able to manipulate this formula and completely get rid of the massless particle information, and just by adding a simple term which is written here, and which is only like you have to add this term where the pi is the total incoming momenta, pab is the total outgoing momenta carried only by the massive particle. So all the massless particle informations can be thrashed away by just adding this particular term. So this is much more simpler formula. And also another interesting feature of this formula is that for Weinberg soft factor, if suppose two objects are passing through each other, like for example the bullet cluster case, when two galaxy cluster passes through each other, there is not much deflection, then this Weinberg soft factor actually vanishes. On the other hand, even if there is not much deflection, this 1 over u tail coefficients still are non-vanishing because they adds up the ingoing and outgoing contributions, they just basically adds up here. So this is a nice feature. So even in those cases, if the static gravitational memory is not present, but this tail gravitational memory are still present and should have observable effect. And just to mention, in a very recent nice paper, actually Campiglia and his collaborator tried to give a physical understanding of why this massless information can be rewritten in terms of massive information using some nice log translation, which is some pure gauge information recently has been established. Okay, so now, so this is all about a mu nu and the 1 over u tail. Like, can we able to compute the higher order terms? And we also computed, for example, this coefficient f and g, which are also universal and determined only by the momentum of the ingoing and outgoing particles or objects and the direction of gravitational wave emission, which generate some subleading tail memories. We also computed this d and e, which are in general not universal from the soft factor prediction. However, they have a post-Minkowskian expansion, and at the leading post-Minkowskian order, we can compute them, and they actually carries the information about the spin and the orbital angular momentum of the scattered object for the first time. So this, if you can observe this d and e mu nu, from there you can able to extract the spin information of the scattered object, which was not possible from the earlier terms. And again, for all these formulas, the massless particle information can be rewritten in terms of massive particle information for all these coefficients. Okay, I'm not giving the explicit expressions for f and d, g and e's, but okay, those are very complicated, so I just thought that let's not give them. So now one can ask, like, can this series really, can one derive all order expansion, which are like the terms which I was explaining, like omega to the power n log omega to the power n plus 1, or in free time space like log u to the power t over u to the power t plus 1. Can we able to get all the terms in this expansion because they are expected to be universal, and can one able to resum them, for example? This is a very nice question, and we are still making progress for the case of gravitational wave waveform computation to all order form. For the electromagnetic waveform case, instead, like when the charged particle scattering event and like they are having some long range electromagnetic interaction, we completed this electromagnetic waveform computation and put out, I think, in January. And there we also saw that for 2 going to 2 charged particle scattering, one can able to resum all this series, and we can give a resum expression for this all order soft factors. Okay, and also just to mention, like, not that all of these results are derived from S matrix. Instead, also we set up some classical derivation considering giving both ingoing and outgoing data for a classical scattering setup, which I was showing at the beginning, and tries to solve Einstein's equation and the trajectory equations iteratively in large time, and to derive all these formulas as well. So those give some independent derivations of all these formulas. So this, okay, now once we have these formulas, we can ask are those physically observable? Do they have some observational signatures? So for that, we tried to do some order of estimation of gravitational strain for some kind of events, like for example in core collapse supernova events which happened in 1987 in our own galaxy, which produces some neutron star. We took the data and tried to estimate, say, what is the 1 over u tail contribution, whether it gives some strain which is inside the current resolution of the detectors. And it turns out that this computation for, say, core collapse supernova or this hypervelocity star produces order 10 to the power minus 23, which is actually very close to the current LIGO gravitational wave detector. And however, the time scale, however, the LIGO only focuses on the merger phases and don't see this kind of events, so it has not been observed yet. But we hope to observe in LISA, if there are some future such kind of events happens, because this order of magnitude will be in OL reach with the resolution of the LISA, which will be placed, I think, by 2040 by this European Union on space. Yeah, I hope that it should be observed. And also one can ask, what can we able to say something about black hole merger problem using this scattering amplitude waveform results. So if you want to treat this black hole merger inside this scattering amplitude avenue, then basically what you have to consider is basically the black hole binary was a single bound object which basically decays to a final black hole with some massless gravitational radiation. And in the cases where basically there is single massive object in the final state and single massive objects in the initial state, what happens is that all these coefficients, the tail coefficients, this 1 over u and the log u over u square coefficient basically vanishes due to cancellation between different terms, which actually provides some indirect proof of Price's law, which exists in general relativity, which tells that for a merger event, after the quasi-normal modes, that power law tail should start from u to the power minus 2. So this is consistent with the Price's law prediction, and also gives an independent proof why the earlier the tail terms 1 over u or log u over u square don't appear in the case of merger events. Okay, so this finishes the first part of my seminar. Maybe I should stop if you have more questions.
Any questions? Yeah, one.
So just wanted to clarify. So the 1 over u means that it goes like 1 over time in real time also, right?
Yes, it's the 1 over retarded time. So the u is the time passed after the peak of the gravitational wave reaches to the detector.
Okay, all right. Yeah, thank you.
Okay, you can continue.
Okay,
I have one short question. This is Ravindran.
Okay, please go ahead.
No, I just wanted to ask you, this analysis is kind of a tree-level analysis, or it is a kind of a quantum?
So this is really all loop order estimate. This is the statement from the from the quantum gravity side. It's a all loop order statement in a perturbative quantum gravity, and from the classical statement, these are really
Where is the loop information contained actually?
Exactly, loop information. So this log omegas actually comes from the loops. Classical contributions, tree-level contributions don't give the logs.
Okay, but this is single log means doesn't it mean that it is a leading order in something?
Yeah, it's basically this, as I was maybe I should show this. As you see, this B coefficient is order Newton constant square.
Yeah.
So this is just information about the one loop effect.
Oh, it's one loop effect actually.
Yeah.
So all order in means actually it's not all order in coupling, it is all order in.
Yes, so what happens is that since in gravity, Newton's constant is a dimensionful parameter, so what happens is that G times the mass of the particles and omega is the soft frequency, they come together as a combination to make it dimensionful. So if you expand in Newton's constant, basically it gives extra power of omega, which is the soft expansion. And then at each loop order, since there is no other collinear divergence in gravity, gives one extra power of logs. So the expansion, if you see from the tree level, which is 1 over omega, now it goes like, it's expansion compared to that, it's like omega log omega order, because like loops basically has the same effect as like the omega expansion in gravity. Yeah.
Okay. So it's a one loop
exact
exact.
result.
Okay.
Exactly.
Okay.
Exactly.
Okay.
That's the statement.
Okay. Thank you.
Okay.
Yeah.
Thank you. Okay. Maybe I should proceed. Just to ask, like, how, like, in time.
Yeah, you have 20 more minutes.
Okay. Okay. Thank you. So now we'll talk about bootstrapping renormalization group flows, which is some way of studying quantum field theory in a non-perturbative setting. And maybe I'll treat, like as I maybe mentioned at the beginning as well, I'll consider quantum field theory in the Wilsonian picture. So any local unitary quantum field theory can be non-perturbatively defined as a renormalization group flow between some UV fixed point and IR fixed point, and these fixed points we assume to enjoy conformal symmetry, and possibly people are already familiar with what conformal symmetry is. I won't describe, but now if you start from UV CFT and deform by some relevant deformation, so relevant deformation is basically turning on some operator with which has scaling dimension less than the space-time dimension. Okay, and if you do that, you basically explicitly breaks the conformal symmetry, or you can give vacuum expectation value to some scalar primary, by which you can able to break the conformal symmetry spontaneously. Whatever way you do, it triggers a RG flow, and at very low energy it reaches a IR conformal field theory, and it could happen also that the IR safety could be empty if the quantum field theory is gapped. Okay, so this is the setup of quantum field theory I will consider for my bootstrap approach. Very nice. So now we have to identify some protected observables, possibly good if it is a scattering amplitude. And to do that, what we do, you'll start with this UV CFT with relevant deformation and introduce some background fields. Let's call them the JI, or the background fields. And then suppose we integrate out the massive degrees of freedom along the RG flow. So in the IR there will be IR CFT, but that will also couple to the background fields I introduced. And since I also integrated out some massive degrees of freedom, it will contain some effective field theory only involving the background fields, which knows about what I integrated out in terms of their Wilson coefficients. Very nice. So now I'll start with this full IR action and try to compute some observables involving these background fields and try to see whether any observables are protected, in a sense, are only determined by the UV CFT and IR CFT data and don't know anything about the details of the RG flow, how we deform it, or whether there has been multiple fixed points in between the RG flows, and many other complications could be there, or there could be multiple RG flows between two fixed points and many other things could happen. So to find such kind of protected observables, we introduce two kind of sources, at least for the sake of this seminar. So one I'll call the dilaton. So the dilaton is introduced to compensate the explicit conformal symmetry breaking near the UV. So how to do that? So suppose if there are some mass parameters involving in the deformation, you have to just basically consider this mass to be a space-time dependent coupling and introduce some while invariance. So basically you scale mass by some mass times dilaton, in a sense, to restore the while invariance if you put this theory in a curved background. And the graviton is basically the quanta of the conformally coupled curved background. So what we do, we take the UV CFT with the relevant deformation, and then we first placed in a curved background conformally coupled to it. Since there is a relevant deformation, it breaks the while invariance, but we can restore the while invariance introducing the background fields dilaton. This is the trick which we can do. Now the full theory which is compensated and placed in the curved background is while invariant, but up to some while anomaly, because the UV CFT could have a while anomaly. So then what is this while anomaly, or sometimes we call it a trace anomaly of a CFT? So as I was telling, CFT in a curved background is not while invariant, but it has some trace anomalies. In a sense, if you integrate out the CFT degrees of freedom and define a connected functional, the while variation of this connected functional, which is proportional to the 1-point function of the trace of the stress tensor, is non-vanishing, but it is determined in terms of some curvature tensor square. And in 4 space-time dimension, there are 2 such coefficients, which basically tells you how the non-invariance, non-while invariance of the CFT happens. And these 2 coefficients we call A and C. And this E4 is the Euler density, and this W square is basically the while tensor square. Very nice. And this A and C are, we call the while anomaly or the trace anomaly coefficients. Often we call A anomaly, C anomaly. So this A and C are just not the fact that they appear when we placed a CFT in curved background, but those are actually proportional to the central charge of the 2-point function of the stress tensor in a CFT in flat spacetime, as well as they can be read off from a combination of OP coefficients from 3-point function of the stress tensors. So those are really some UV CFT data, because those are the OP information of the 4-dimensional CFT. Very nice. So now, as I was telling, take this CFT placed in a curved background, couple it while invariant way, then deform the theory and restore the conformal symmetry breaking by introducing dilaton as like a spurion analysis. Now the theory is completely while invariant up to this while anomaly term controlled by the UV CFT, and now flow to the IR. So what happens is that this trace anomaly matching condition in the IR will put some constraint in the effective field theory you got by integrating out massive degrees of freedom. And the effective field theory you got will have to satisfy that it has its while invariance will take care of the difference of the UV CFT anomaly and the IR CFT anomaly, and the difference of UV CFT C anomaly and the IR CFT C anomaly coefficients. Where I denoted this delta A is the AUV minus AIR, and CUV minus CIR is represented by delta C. And here just the tau, or sometimes I will call phi, to be the dilaton field, and G mu is the metric. So this is the constraint the effective field theory in the IR you got has to satisfy just from the trace anomaly matching in the RG flow picture. And now one can solve this equation and can write down a general form of this effective field theory.
Excuse me.
Yes, please.
Using this compensating dilaton field, you get rid of these terms, but what happens to the unitarity of the theory? Is it still preserved, or it went out?
No, it is still preserved. So the dilaton I will treat only as a so the dilaton I will treat as only a probe field. So they don't run in the loop or anything. I'll just think of this dilaton as a source for the trace of the stress tensor. So it just as a source field for the RG flow, but I just gave it a while variation property. That's all. So they won't.
But the cancellation is happening with a classical term, is it?
Which cancellation?
If the dilaton doesn't have any quantum corrections.
Yes, yes.
But you arrange the cancellation, which is a quantum correction.
Oh no, this is a classical. So okay, so maybe I should make, maybe I was not clear.
Okay,
maybe sorry. Maybe let me make it clear.
Could you please clarify that?
Yes.
Thank you.
So when I turn on a relevant deformation, I classically break the conformal symmetry. This is understood, right? So it's just, or classically, like in a sense, it's just a explicit breaking of conformal symmetry, which will affect also quantum mechanically. But the anomaly is a contribution which only is quantum mechanically. When you integrate out the safety degrees of freedom, you see the anomaly. So I won't able to restore restore the anomaly, or the anomaly contribution to the while non-invariance property. What I can restore is basically due to this relevant deformation, which breaks explicitly the conformal symmetry, that I will restore using the dilaton. But the anomaly contribution still remains because it's a quantum contribution, and dilaton is just a classical external fields, you can think. And this is what I am doing. Is it clear or?
Not quite, but you can go on.
Maybe I can, if it's possible to write something. So what happens is that, suppose I turn on some operator with scaling dimension, it's not, some operator O with scaling dimension delta with some coupling lambda to deform my theory. So now under while transformation, so there is some metric square root over metric G. So under while transformation, this transforms like, say while transformation is like scaling G mu nu to be to the power 2 sigma G mu nu, or where the operator scales like e to the power minus delta sigma times O. So this is not while invariant, but what we do is basically we rescale this M to be M times omega, and this omega is like a spurion field, and whatever the while transformation breaking happens due to this explicit conformal symmetry breaking, I will give a while transformation property for this omega, so that now omega times m whole to the power 4 minus delta times the deformation is while invariant. This is the simple trick I am doing to restore the while invariance corresponding to this relevant deformation. But the anomaly is still there, and it's still there along the whole RG flow. I don't know whether it's still clear. Yeah.
No, the point being that the extra term that you added, how do I know that that preserves unitarity?
Oh, it's like the sources, right? When you have, say, some global symmetry, there is a current, you just gauge it by some gauge field mu, right, to which is a non-dynamical gauge field, and give a gauge transformation to it, right? So once this gauge field is non-dynamical, it's like along the RG flow, still the unitarity is still intact, right? These gauge fields will only appear as external legs, never runs in the loops. It's just I am treating this omega or this dilaton to be just a source for the trace of the stress tensor, which basically breaks the conformal symmetry. But I'm not touching the whole entire RG flow anyway. It's just an external source.
Okay.
Yeah, it's
continue.
just. Okay, so then basically the restoration of the explicit conformal symmetry breaking has been done. The anomaly term still remains, and that will show up in the IR. So one needs to use this anomaly matching condition while constructing this IR effective field theory. And I won't show the explicit expression of this effective field theory, how it is written in terms of graviton dilaton. Instead, using this effective field theory and also the couplings of the IR safety degrees of freedom with the background degrees of freedom, taking care of everything, we can try to find that whether we can able to identify some observables which are protected. And one of such observables has already been found by Komargowski and Swimmer, where they are able to show that the 4 dilaton scattering amplitude in low energy expansion, that is in 4 power in momenta expansion, actually is protected. So if the IR effective field theory usually has also some Wilson parameters, so they cancels out when you consider the scattering amplitude. And just keep remember, this is a scattering amplitude involving dilatons, but still the dilatons are non-dynamical, that is they don't runs in the loop. So they just probes the trace of the stress tensor along the RG flow. So you can recast this 4 dilaton scattering amplitude in terms of really a combination of 4-point function of stress tensor, 3-point function of 4-point function of trace of the stress tensor, 3-point function of trace of the stress tensor, 2-point function of trace of the stress tensor, a particular combination along the full RG flow, and then take the soft limit. So this is just a trick to probe the deformation of the probe the trace of the stress tensor, basically this dilaton. And so now once you have this effective field theory, and then basically you do a small momentum expansion, what you will realize is that the 4 power of momenta, all these informations about this undetermined like Wilson coefficients and possible coupling of IR safety to the dilatons, all they cancels out, and you find this 4 dilaton scattering amplitude is universal at 4 power in momenta, and it is only determined by the difference of the A anomaly value between UV and IR. And then once you have this, you can use the unitarity basically to prove that this AUV is greater than AIR, and which proves the famous A theorem proposed by Cardy. So we goes on and we try to see whether any other such kind of observables also existed. And what we found is basically there is another observable you can consider is basically a graviton dilaton scattering amplitude, and look for the helicity flipping part of this graviton dilaton scattering amplitude, which basically is telling is that in the conformal symmetry breaking vacuum, you are basically sending a graviton and looking at its helicity flipping part. And if you do that at 4 power in momenta again, this is again it turns out to be universal and completely determined by the difference of the C and the A anomaly coefficients. And now you can invert this relation to write a dispersion relation, and from there you will be able to see how exactly this combination delta C minus delta A counts precisely the degrees of the spinning massive particle degrees of freedom which you integrated out along the RG flow. Okay, this gives a physical interpretation of what delta C minus delta A is. Very nice. So now once we identified this scattering amplitude, we can ask, can we able to use those in the bootstrap framework to answer some non-perturbative questions. And one of these questions I will answer is basically, suppose consider a massive quantum field theory with the lowest lying state is basically the massive particle with some mass scalar m, and we can ask what is the minimum value of the AUV which can flow to such a gapped quantum field theory. Okay, and so here, to answer this question, we need to set up a bootstrap problem involving multiple scattering amplitude, where two massive particle going to two massive particle, massive to dilaton, and 4 dilaton scattering amplitude, and we have to non-perturbatively parameterize them, use unitarity, and finally run some numerical SDPV program. So I have all these details, but I don't think with the time being I won't be able to explain, but I will show the result. If we run this numerical asymmetric bootstrap program for this setup, the answer we got is basically that this AUB is bounded from below for any RG flow which is gapped, and the stable lowest lying state is basically a massive scalar, and the value is 0.32 times the free scalar A anomaly value. So, and we also played, this is the global minima, and it lies, so we also played with how this minima changes with the strength of the 4 matter particle scattering and where the minima lies, and we were able to find that which is the allowed region for the A anomaly value. And also we can able to plot all the scattering amplitudes lying in the boundary, and as you can see, the strength of the coupling where this minima lies is basically like near -6, and this is basically telling that this is a strongly coupled scattering amplitude. And for such a scattering process, like one can able to see that the minimum of the AUB has bounded. And so earlier it was known that it is like just from the unitarity of the Komogorowski-Swyma, that it is less than, it cannot be less than equal to 0, it has to be greater than equal to 0. But now under assumptions of this gapped spectrum, we can say that it has to be greater than 0.32 times A free, so there is a gap. And also we played with various ways with the scattering amplitudes in the bootstrap.
Sorry, Vishwadeep, this is in what dimension? Is it
in 4 space-time dimension?
4. So is there something else you have to impose about the UV CFT when you do the...
No, here I'm not imposing in the UV CFT. I'm just considering a QFT spectrum. So the only assumption I made is that the QFT is gapped, and the lowest lying lowest lying particle is basically a single massive scalar particle.
You don't make any other assumptions about the next massive particle or anything like that?
No assumption about only. And the other thing I had to assume is that the whole RG flow is unitary throughout. This is another assumption I had to make.
Okay, that's fine.
Okay, yeah. And obviously on top of it, some analyticity crossing and some high energy behavior of scattering amplitudes. Those are the standard like assumptions in the bootstrap program. Okay. I'm not doing well with time. So, okay, now let me tell another bootstrap problem which we address is that putting a conformal field theory in a strong magnetic field. Here I took the conformal field theory in 3 dimensions, so 2 plus 1 dimension, and which has a global U1 global symmetry. Okay, so now if we place such kind of a conformal field theory, as you know, due to various even free theory random level problems, it becomes gapped, and the mass gap is given by square root over a magnetic field in 3 dimensions. So the IR safety is again empty. So now we would like to ask question that can we able to put some constraint on susceptibility transport coefficient at strong magnetic field. Okay, so and here you can think again this as a RG flow, as I was mentioning, by turning on a current operator with some mu, and mu is basically takes a configuration which provides you the constant magnetic field. But since the IR is empty, we introduce some set of background fields, and one of the background fields is basically the fluctuation about this constant magnetic field background, and another is basically we place this theory again in a curved background or conformally couple it to a curved background. And the whole goal of this thing is basically this mu basically takes care of can be thought of as the source for the current operator, and again the metric can be thought as just the source for the stress tensor operator along the RG flow. That's the only purpose of introducing these background fields. However, this helps enormously because now we can use while invariance to write down the effective field theory in the IR, while invariance and gauge invariance. And they involve writing the derivative expansion of the effective field theory in terms of field strength and some while invariant combination of metric. And we can write down this effective field theory like pretty high order in derivative expansion, classifies all possible effective actions up to integration by parts one can write down. For example, at 4 derivative order there are 28 such kind of actions, and 2 derivative order 3, and 0 derivative order there is only 1. And then finally, once we wrote down the connected functional using while invariance and gauge invariance, we can expand this gauge field about the background field given by the constant magnetic field and the fluctuation to find the effective action. And once you know the effective action, from there you can be able to compute various observables. For example, the current correlation just by varying with respect to 2 times with respect to gauge field. And since the Lorentz symmetry is broken, there are 2 such kind of spectral density, which I am calling the ρ1, ρ2, and they have expansion in large magnetic field or equivalently small momentum. So it's expansion over momentum square over magnetic field. Similarly, the other coefficient. And we also can compute the other correlators like the JT and TT in the large magnetic field expansion. We can also place this theory on a cylinder by conformally mapping it and put in a magnetic monopole background and compute the free energy, and from there also compute the susceptibility, magnetic susceptibility, which is again given in terms of the same EFT coefficients. Okay, the C0, C21. And finally, now we have the observables. We can ask whether we can be able to use some kind of develop some kind of bootstrap technique. And since the Lorentz symmetry is broken, obviously the standard all the bootstrap technique fails. So we had to redevelop, like for Lorentz symmetry breaking case, how one can develop this bootstrap program. And here we only did for only the in terms of 2-point functions and using retarded Green's function because the time ordered Green's function is not now available. And starting some analyticity, crossing another property, and we can write down some dispersion relation with the high energy behavior controlled by the UV-CFT. We are able to finally found that this following relation has to be satisfied. So these are some frequency space current correlators, current stress tensor correlators, and this following matrix have to be positive semi-definite in the regime when the momentum is given by frequency and it's parameterized by some unit vector whose modulus is less than 1. And each power in omega L expansion where the L runs from 468. And from there we derive bounds on the Wilson coefficients, which in turn gives the answer that at strong magnetic field, any 2 plus 1 dimensional UV-CFT with global symmetry will always behave diamagnetically. That is, the magnetic susceptibility will be negative. And also we put bounds on various ratios of Wilson coefficient, which in turn provides a bound on the magnetic transport coefficient in strong magnetic field with some allowed and disallowed region. And we also explicitly computed for some explicit theories and put numbers in the allowed region as well. Okay. So this is the statement, like using bootstrap, you can be able to answer various questions more generically, irrespective of the theories. Like for any generic CFT with U1 global symmetry in 2 plus 1 dimension will behave diamagnetically. And this is the kind of answers we can do it. So now, yeah, I just want to ask how far we can go. I have just the future directions.
Yeah, you just take your time and finish it.
Okay, thanks for allowing me. So, okay, so now one of the future directions which I would like to explore is that till now, for the first part of my seminar, I mostly talk about like using scattering amplitude for some classical scattering setup, how one can derive the gravitational waveform. However, the recent era of gravitational wave physics mostly focuses on the binary like merger cases and try to find the waveforms for like binary systems. So one can ask the question: Can one able to use these gravitational waveform results which we derived for scattering event and go to give some information about the in spiral, at least the in spiral phase when the two black holes are separated, and can one able to tell something about the gravitational wave from there? Okay, so this question is not that I am asking for the first time. For conservative observables, like for example the momentum impulse or scattering angle, this is the kind of observables Rafael Porto and collaborators already developed an analytical continuation method to extract the bound state information from scattering events. However, when there is a radiation involved, like the gravitational radiation, then this analytical continuation fails because it don't work just perturbative order. So the roadmap which I would like to explore here is basically, once we have this gravitational waveform which is all order expansion in the frequency expansion, which I already did for the electromagnetic and currently doing for the gravity case, we can resum for going to two cases and develop an analytical continuation in this frequency, in the frequency plane, and able to go from scattering event to a bound event. And this is not surprising, because as we learned possibly in classical like classical mechanics, that from hyperbolic orbit to elliptic orbit, one have to basically change basically the sign of the energy from going to one state to another state. But now the certainty here is that on top of it, we have to take care of the radiation, outgoing radiation, and develop this analytical continuation method. But I think once we have this resum formula, one can able to play with it and develop this analytical continuation method to extract in waveform information of the in-spiral phase of a binary merger, starting from this scattering event waveforms we derived. Another interesting problem is basically, currently it is kicking up, is basically the celestial holography problem. So where what one does is basically one consider a quantum gravity theory in asymptotically flat space-time, and then try to think whether one can able to write some theory on the null boundary, and which is dual and knows everything about the quantum gravity theory in flat space-time. Though I'm not sure it knows everything, but at least it is roughly clear that it knows about the soft sector of the quantum gravity theory. Okay, and what people did till now is basically that writing down some tree-level soft theorems in the celestial basis, going to Mellin space and interpret this soft theorem expression in terms of some some symmetry properties of the celestial correlators, and written down some OR identities. However, we derived all these loop corrections to the soft factor, and there has not been much progress on developing how these celestial soft factors tells about what kind of symmetry on the celestial CFT, what are the OR identities. For example, as I was showing, the soft factors has some multi-particle sums, and those informations basically, if you try to translate with the celestial CFT picture, the corresponding currents basically are non-local. The OR identity they satisfies are non-local, and at a time talking to two of the celestial CFT operators, not just one, as we see in the usual CFT picture. However, we are developing this tool with Samik, and now we can actually discover some new kind of fracton CFT algebra, and possibly it will also set some new light on two-dimensional CFT when there are some dipole moment is conserved, and one can able to develop some, there is this fracton phases in in condensed matter physics, and also high energy physics people are developing, but one can also extend to it, include the conformal symmetry, and they have some non-trivial OR identities which kind of showing up if we study these loop corrected soft theorems on the celestial sphere. So this is some development I am still currently doing and want to pursue. And another thing which I am kind of more influenced at King's and currently pursuing is basically all this development I was talking about, this bootstrap or this anomaly renormalization group flows, are only for the bulk renormalization group flows. But suppose what happens when there is a defect, some p-dimensional defect in a d-dimensional bulk, and can one study some RG flow picture on the defect, introducing these background field methods, and also develop some bootstrap bootstrap arguments. And this is one of the directions which I am kind of progressing, and it looks like the simplest candidate to study this is basically the trace anomalies or the scale anomalies associated with the displacement and the tilt operators, which are some protected operators on the the defects, and studying their renormalization group flow gives some kind of protected observables, and possibly it will have some bootstrap implication as with time. And another promising direction, which is I think still a long-standing puzzle, and so the asymmetric bootstrap program, what I told you, mostly works for massive quantum field theories, because even for the massless quantum field theories, the analyticity and various assumptions what one makes to bootstrap basically are invalidate. And on top of it, when the massless particles are photons or gravitons, there are these in 4 dimensions, there is this infrared divergence issues, because while constructing the asymmetrics, one usually assumes that the asymptotic states are states of the free Hamiltonian and the interaction dies of at infinity, which is not true, as we know, in 4 dimensions. While studying the soft theorem, there we resolve this IR divergence puzzle. Now the question comes, if we take asymmetrics to be the concrete observable, we should make it IR finite, and because if we want to take it seriously for the bootstrap program. And there has been few proposal of how to do this. Some of the proposal tells that you have to replace this pre-Hamiltonian by asymptotic Hamiltonian. However, all these proposals are still not concrete because some of the cases the states are non-normalizable. Some of the cases you need explicit IR cutoffs, all these things. So the goal will be to first develop like a procedure which is a S matrix, which is a IR finite S matrix, and which my feeling is that from our soft theorem analysis, it's basically the G graviton or the G photon S matrix is basically what is the IR finite S matrix, as we also see from the soft theorem analysis. And then finally study their analyticity, crossing and unitarity property at least up to few loop orders in perturbation theory, and then finally make those assumptions non-perturbatively, try to do bootstrap program. Okay, and obviously using this bootstrap program now we can ask very ambitious questions. For example, like what will be the UV completion of 4-dimensional quantum gravity S matrix in a full non-perturbative setup, which has not been answered yet because of this IR divergence issues. And maybe using this quantitative analysis, we can able to put bounds on various effective field theory coefficient in turn, which will bound, if we think of string theory is the quantum gravity, it may put bounds on the various compactification length scale involved going from 10 dimension to 4 dimension. So with this hope, let me conclude, and thanks for giving me time and allowing over time all these things.
Okay, thanks. Any questions?
Can I ask a short question actually?
Yeah.
Yep.
Maybe after everybody finishes, or
You can continue.
okay. So I mean, in the first part of your talk, you mentioned about understanding this gravitational wave trends by looking at some of the ideas from soft theorem.
Yes.
Can you also make statements? I mean, you mentioned that you can actually do a similar thing for QED.
Yes.
Is it with the matter or without matter? Actually, when is it
with matter. So we already did. So all these results which I showed to you already, we did all this for the QED first to get the idea before doing gravity. So all these results existed for QED, and those are really some massive charge particle scattering with some electromagnetic interaction.
What is the new thing that you get which is not already known in QED context actually in the case of QED?
So for example,
QED is one of the well-studied field
that's
theories.
a very good question. So one of the
and what is that new that we did not know, now we know about?
That's a very good. So one of the new thing, at least we did in, like, we put out the paper in January, is basically that classical electromagnetic Bremsstrahlung for like some charge particle scattering can be resummed at all order in frequency expansion, and we gave a resummed expression. So it was not known earlier, even like for the charge particle scattering, you could have a resummed Bremsstrahlung in frequency space.
But so maybe there are similar results not in frequency, but I have seen, people talk about resumming soft photons. You can find in even Peskin's book, and also in many other contexts. This
right. But I don't know whether frequency.
It's only the variable difference, is it?
Yeah, it's just the frequency. So you see, the frequency expansion also corresponds to the charge expansion. So it's a really all order charge expansion. It's like all loop expansion resummed expression.
Some resummed result actually. Yeah, there are plenty of resummed results in QED, but maybe there are some connections.
There could be. So these are the kind of new things, and also some electromagnetic memory you can get. Like for example, the analog of gravitational memory I told. So for charge particle scattering, there are some prediction of electromagnetic memory also. And recently there has been some PRL papers which I saw. They basically putting out a setup where one can be able to observe this memory. So if you can put so there will be some enhancement of this memory due to some putting in a material, and they set up some, they can observe actually this analog of gravitational memory, which is the electromagnetic memory, in a lab, and those predictions comes from the soft photon theorems.
Okay, thank you.
Yeah.
And what about non-abelian gauge theory? You have some results on that?
That's a very good question. So what happens? So for example, in QCD, if we try to run the same program and say derive the soft expansion, what happens? The Weinberg soft factor goes like 1 over omega, like the analog of Weinberg soft factor in QCD. I don't know what the name is. So if you go one loop, it goes like log omega by omega. So it's more dominating than the 1 over omega. And if you go higher and higher loops, you will get that it is dominating over the Weinberg soft factor. So this is just saying that at large distance, you really don't have like soft gluons, and they basically, this feature is basically showing that at large distance, or the soft radiation for the gluons don't exist, because higher and higher loops gives more leading and leading contribution to your tree level result, and this soft expansion basically breaks down for all loop order QCDS matrix.
QCD, you're saying that there are no soft theorem.
There is soft theorem at perturbative order in Yang-Mills square, but if you consider Yang-Mills square to be finite and do only small omega expansion, this is what we are doing here, QED or QCD case, where suppose Newton's constant is constant, we are not considering this is a small, but omega is only the expansion, then you will see that this is infrared catastrophe in QCD case. You will get more overleading corrections from higher and higher loops.
That is expected, no? Because if you are looking at amplitudes and emissions,
yes,
you don't, amplitudes are ill-defined in quantum field theory, if it's massless. Even pure gauge theory, amplitudes are ill-defined because there are quantum corrections.
Okay.
So the infrared divergence that you mentioned. Only certain infrared safe observables are
right. But the soft expansion, I think, if you now, like for the gravity case, now if you define an inclusive cross section, but considering these gluons are soft. So I think what is happening is that considering this gluon is soft and going higher in perturbation order, this basically somehow breaking down that long distance you cannot treat gluon as to be the fundamental like particles, like it really don't reach to null infinity or like time very far, because this because I think the infrared issues in QCD is much more stronger compared to gravity and QED case.
Okay. And you said actually, at that, maybe if I can add one more question, time permits. Okay. You mentioned that, you have this puzzle, that amplitudes are divergent and things like that. Why do you call it puzzle actually? Even in QED, if you take a 3-point function, when photon is massless, that's the case.
Yeah, that's
no divergences actually, no? If you just take a 3-point function, if you
I completely in agreement with you. Yeah.
So why actually?
Yeah, it's not puzzle.
Because you are looking at some part of some observable or whatever physical quantity.
Let me
looking
clarify.
At Green's function in field theory are all ill-defined actually in the infrared, because photon is massless in case theory.
I completely agree. Yeah, let me clarify my points maybe.
It's not a puzzle, no?
Yeah. So
what is there to solve actually?
Yeah, so let me answer in the following way. So, like as you told, any exclusive observables we compute in massless theory are infrared divergence, and that's okay, because what we observe is the inclusive observable, say inclusive cross section, for example. So you may tell what I am solving here. So the question I would like to solve, for example, the soft theorem, which is a factorization of S matrix. When I am talking about soft theorems, I am taking S matrix to be a serious object, because I know that S matrix are IR divergent object, but the soft factors which are related to the gravitational waveform, which are observables. So the soft factor should still be IR finite object, because it is an observable, though the individual S matrices are not. So that is one of the puzzle we solved, that while deriving soft factor, since it is a ratios of two S matrix, so in the ratios of S matrix, you can able to factor out the IR divergent pieces and still can able to extract a IR finite piece. So all the observables have to be IR finite, not the S matrix. This is my statement. But now let's come to the S matrix bootstrap program. S matrix is like an exclusive observable, so it is in a sense IR divergent, and you may tell, okay, it's not an observable, what are you doing here? So here the point is the following. So if we want to incorporate unitarity, causality, analyticity, all these properties, those are well understood in terms of S matrix. So the question I would like to ask, can one able to define some inclusive S matrix with which I can take in which I can consider like some integrating out some massless radiation flux in terms of some dressing of the external particles, and define a inclusive S matrix and study its analyticity crossing properties. Since I know now this analyticity crossing property of this inclusive S matrix, can I able to use this to constrain the some low energy properties, assuming those assumptions. If I have only inclusive observables like cross sections or other things, I won't be able to play with these physical principles. So that's why I like whoever takes S matrix to be very seriously and use their property to constrain quantum field theories, I have to first define an inclusive S matrix which is IR safe, and this is the goal. So it's basically, as you told, all the observables have to be IR finite, but not really this S matrix because it's not well defined. I completely agree with you. But the thing is that some of the properties can be derived, like the soft theorems or these bounds, from the S matrix. So it is a useful tool still to use those, though IR divergent, but one can be able to systematically factor out the IR divergence and consider those in terms of some inclusive process, and then finally use still this S matrix to derive many results which was not known earlier, and interesting progress one can make. This is kind of the attitude I take, at least. Yeah.
Okay, thank you. Yeah.
Any more questions here? Okay. Okay. Thanks a lot, Biswajit.
Thanks.